Hello, and thank you for joining us. Today's webinar topic is Defining Green Chemistry with Teledyne Lehman Labs QuickTrace M7600 Mercury Analyzer. Our presenter today is Jeff Forsberg, Mercury Technical Manager for Teledyne Lehman Labs. If you have any questions, please feel free to submit them throughout the presentation, and Jeff will get back with you after the webinar concludes. This webinar is being recorded and will be available within a few days. Okay, now I'm going to turn it over to our presenter, Jeff Forsberg.
Thank you. I'd like to say thank you to everybody who is joining the webinar today. So defining green chemistry. How do we define green chemistry? Well, to me, I define it as saving reagents, saving waste, saving money. So all three of those items would go into defining green chemistry for the M7600. So this is the M7600 here, parasolic pump, gas liquid separator in here, and this is coupled with the ASX 560 auto sampler. So in order to discuss the green chemistry and how we accomplish that with the M7600, I'm going to give you a short background on the system, how it works, and then a little segue into the new pump tubing, which is how we accomplish the green chemistry, and then the ease at implementing the green chemistry via the QuickTrace software. And then we'll discuss some of the results from the testing, and then also the analytical results as well that we use to implement the new tubing harness. The QuickTrace M7600 is our most versatile system, so you can actually hit instrument detection limits, method detection limits of less than 0.5 ppt, nanograms per liter. It is sensitive enough to work with EPA 245.7, but we don't recommend it because in certain cases you can form bromoform, which will give you a false bias in the results. It could be anywhere from 10 to 200 ppt of false bias on samples when that's formed. But without that, we can easily hit 1 nanogram per liter in less than 90 seconds with this system. The normal usable range on the system is 0.5 to 500 ppb, and that's with our standard tubing. For the new tubing, which we're going to discuss here shortly, it changes just slightly. The bottom end goes maybe around 0.7 ppb, and the higher end can increase up to about 700 ppb or 0.7 milligrams per liter. And we do all this without any hardware changes. So you're changing the software ranges, you're bringing in the new tubing, and you're all doing it through the software without making any hardware changes at all to the system. The system is double beam optics. We have a lamp stabilization. So there's a compartment where the lamp is and it's heated. It's thermally stabilized. We have a system in there called EOFM, stands for Electrical Optical Feedback Monitor. So this automatically adjusts the lamp energy as the lamp ages. This process will allow you to keep your method detection limit, your instrument detection limit, your lower limit of quantitation at a steady state as the lamp ages. So it keeps the same energy onto the detector at all times. The carrier gas is controlled by a mass flow controller. You can either use argon or nitrogen. So it's a very stable gas flows with the system. Liquid separation, gas liquid separator. So it's a center post design. Large reaction surface area to the small liquid volume. That gives us rapid evaporation of the mercury into the gas stream. Increased efficiency increases throughput. That's a stable liquid film flow. That is going to give us reproducible signals. And with reproducible signals and the stability of everything, that now we have precise results. So low to ultra trace method detection limits. Since it's a center post design, that means we don't have a reservoir of liquid, so it's not bubbling. So it's constant removal of liquid through the drain and waste lines, and that gives us a fast recovery of and mercury spike. Let's say we spiked it with the 4 ppm or 1 ppm. So within 4 minutes, the sample is basically back down to baseline or a non-detect. Also, so it's non-foaming. So if you're running biological samples, you don't have to add anti-foaming reagents. And it has a built-in overflow that will detect any issues with liquid flow. For example, if you happen to hook the peristaltic pump tubing for the waistline up backwards rather than draining, it would fill. The system would shut down. It would stop the peristaltic pump and tell you that you have an issue with the waistline. Now we segue into the peristaltic pump. So this is a 4-channel, 12-roller pump. Ultratrace detection limit, so that hasn't changed from the original pump tubing harness. Samples not consumed, that's still the same. You can dial in the flows for higher ultratrace concentration. That's also, there's no change there. We do have a wider dynamic analytical range, as I stated earlier, than the standard tubing. Liquid uptake is still as little as approximately 1/2 ml. That's 5 seconds of dip into the sample tube with the probe, to a max of 10 mL per minute, and that's at 60 seconds at max pump rate. The max pump rate for the standard tubing was about 15 mL per minute on the standard tubing. So the autosampler configuration that can be packaged with the system is either the 560 or the 280. The 560 is a 4-rack system and the 280 is a 2-rack system. You also have the option to run without an autosampler if you only have 1 or 2 samples a week. Calibrate using the probe. You manually move it to and from the rinse station and to and from the standards and or samples. So there's 3 easy steps for changing dynamic ranges. What affects the dynamic range in a continuous flow system? So it's got gas flow, pump rate, and time in sample. Gas flows, high flows are equal to short residence times. That's going to give you speedy results, but it's also going to decrease the sensitivity. But when you decrease the sensitivity, you can increase your dynamic range. Low flows or long residence time, it's going to increase the sample times, but it increases the sensitivity. So if you increase the sensitivity, you can drive the system down to a lower method detection limit and or instrument detection limit. Pump rate, same thing. That's going to increase or decrease the time to the GLS, the HG loads into the system. And then time in sample is basically the same. So it'll increase or decrease the sample load and adjust to a steady state. If you're doing peak height and you want to look at the signal plateau, you want it somewhat flat. If you're doing peak area, you can run the system relatively fast and you just measure everything under the peak itself. So you adjust all 3 settings to achieve the desired results. So here's basically how the system works. It's a dual cell system. We have a reference cell and sample cell. Our stannous chloride is 10% and 7% HCl. The stannous is going to reduce the sample, which is digested, oxidized to Hg2+. In solution on its way to the gas liquid separator. So by the time it gets there, it's already going to be Hg0. The sample gas flows in through the reference cell, flows out of the reference cell, and makes its way over to the gas liquid separator over here in this dual beam system. From there, the reduced mercury or the elemental mercury is going to pass out of the gas liquid separator, go through the Nafion dryer, and end up in the sample cell where it's measured at 253.652. So with that said, on the system, when we take the 4-channel 12-roller pump, the mass flow controller, the gas liquid separator, and everything else that delivers precise solutions with a stable gas flow to the system, you get very, very precise results. So most of the time, we are going to say we're going to get at least 3 nines in almost any range, including the green chemistry range of 0.7 to 700 ppb. Here's an example where we were calibrated from a 1 ppt to a 10,000 ppt or a 10 ppb, and we achieved 3 9s and an 8 9 on that calibration. Now the pump tubing. Okay, so let's dive in here a little bit. So during this process, we wanted to keep all the ratios the same. By those ratios, I mean the reagent and the sample as they compare to each other. So we didn't change anything within the system that, since how it's been operating for so many years under precise and ideal conditions. Let me stop here for a second and get you to look at the part numbers. So part number 15-4308-102, that is the white over here, and that's for the drain. And then the same pump tube number is for the sample. And then the reducing or the stannous chloride is 15-40309-102, and that is red-orange, 0.51 millimeters and 1.02 millimeters for this tubing. So setting the tension is exactly the same as what you would have done with the original tubing. It's also described in the manual. So you load the tubing on the parasolic pump, and then you set the tension to, so it's flowing slowly in the liquid mix line, or not the liquid mix line, but the transfer line, and then it's kind of jerky. So from what we do there is we do a one full 360 clockwise revolution to that tension, and then on that it's the sample line right here. And since those are the three same tubing, you set the tension lever here exactly the same. The reducing agent or the stannous is a little bit thinner tubing, smaller OD and ID, so you turn that in about 1 millimeter further. And once you set it, you forget it. So you never want to mess with the tension for failing pump tubing. Only change the tubing harness and leave the tension the same. And with that, typically what we'll do is we'll break in the parasolic pump tube for about an hour with, excuse me, with DI water and reagent. So once we got in here and we looked at how this pump tubing worked, it actually reduced the sample size by 33%. So we're using 67% of what we would if we were running with the normal pump tubing. But the biggest savings is on the reagent side. We were using 47% of what we would be with standard tubing. So that's a 53% reduction in stannous chloride. And stannous chloride is relatively expensive. So that's kind of where the green chemistry comes in for us, is the reduction in one, reagent and reagent costs. Now, when we looked at the flows, they're very linear. So up here we have the waste, total waste for the system at 50%. It's about 39 or 40% from one to the other. At 80%, it's the same thing, 39 or 40%. And then we have the reducing or the stannous flows. This is a reduction of 53% at 50%, a reduction of 53% at 80%, and of course on the previous slide it was a reduction of 53% on 100%. And also the same thing with the flows. They're 80% here is exactly the same as what the other one was at 100%. So a reduction of 33% or 67% of the original volume. Here's where the savings comes in. So if you're running 8 hours a day, typically on the original tubing, you'd be using 2.74 liters if you're at 100%. With the new tubing, that drops down to 1.29 liters for an 8-hour day. Stannous chloride varies in costs. It could be anywhere from $250 to maybe $400 to $500 for 500 grams. So let's go with the worst case scenario. So let's say we're on the more expensive side. That 8-hour operational day with the new pump tubing, you're going to save $150 US dollars. If we're running 5 days a week, or 260-day year, that's going to save you $39,000 in stannous chloride costs alone. That's $39,000 in stannous chloride costs without even calculating in the reduced waste reduction in costs. Quick Trace software. So now that we know how to set the tubing, how to set it up, how to adjust the flows, we'll quickly talk about what we do in the software. So we have free upgrades, interactive graphics, and that's key, overrange protection on the fly, sample additions, and consumable tracking. So we have peak height or peak area in all systems and all analytical modes, and that really helps you dial in the system for how you want to run it. So we have applications where we run it in, say, 1.5 minutes per sample, maybe under peak height, peak area with a little higher gas flow, a higher pump rate. You can run it in as little as like 45 seconds per sample. We can also export or copy the results, export them right into a Word or Excel document while it's running. That's useful for, say, somebody wants a number right now, they're a high priority or a stat sample. You can pop it in the system, you can get the results, you can do the math on it and get the customer's report. We also have user-defined blank acceptance criteria, which is mainly for US EPA 245.7 and 1631. And those who are accustomed to that method will really appreciate the ability to set the blanks higher than what the method calls for. And it all depends on your region and what the permits are. So our software, we take a pragmatic approach. You have the drop-down window where you can jump between all the main user interface windows. You can hit them from the favorites bar, or also we have pop-ups. So you can navigate through the software by using hidden windows or hidden menus that pop up, and mostly each and every user interface. If there's some white space, you can right click or left click, and you'll usually get some type of pop-up. Here's an example of right-click pop-up menu in the sequence editor. So there's a lot going on here, but basically what I want to show here is if you hover here, you get a pop-up for the auto sampler, so you can point and click. It'll load the tube number, you've got fill down, etc. You got all your weights and volumes and your spike volumes coming down from this menu here. So everything is right here. You can set your units of quantitation, units of weight, units of volume, all right here on the sequence editor. And you can import, export from the limbs here as well. You can also do it from the main file drop down over here. So there's like usually 3 or 4 places within the software where you can get to the same end. This is the Sequence Wizard. Here, this is where we're doing the QC. So everything is drop and drag. So it's, or drag and drop, however you want to say it. So it's really, really easy. Yellow in here, green in here. Here you can create your own. You just right click, set the properties, and once every 10, once every 20 samples, however you want to do it. And then you can bring in your spikes and your CCVs and CCBs and so forth. One thing I must point out here is really, really cool on this software right here is limit QC tubes. So for example, let's say you're pulling 15 mils of sample per analysis, which you never would be, but maybe you are. And then your tube is 40 mils. So you can only go in there twice, and then you'd be running dry. So if you know the flow, the volume of the tubes, and how many samples you're going to need, what you can do is you can limit this. So if I said I'm limiting it to 2, because I know I can only go into that tube twice, it's going to automatically load additional quality control samples in a rack that you designated as quality control, so it can complete the whole run. So if it knows it needs 1 every 10 and you have 50 samples and you can only go in there twice, it's going to load up 2 more continuing calibration, verification, blanks and spikes and whatever you want in there. So it's really a nice feature. And then everything's color coded, so you can take it right to the hood, do a printout, and load up your sample vials. So this software is so pragmatic that we allow you to design your own favorites bar. So you don't have to go with how it comes. You can grab your core right here by grabbing this ellipsis, and you can move it around, and you can set this window or this favorites bar up how you would like to see it, how it works for you. Maybe you want your go button way over here on the left. Maybe you want it all the way over on the right. You can move all these around. So that's really a nice feature. Method development. So we develop methods in real time. Method editor, you have tools where you can define the units, standards, conditions, your auto sampler, and your analyzer timings and settings. Enter your concentrations and rack position for your standards, and then your QC test concentrations and limits. This is all here under Method Editor. And then from there, it looks like this. So it'll enter your standards. You can pause at the end of the calibration if you want. You can have the system send you an email when it's done with the calibration. There's a number of things that you can do in here with Method Editor. So when you're in here and you're under the conditions, there you have your auto sampler and your analyzer tab. Auto sampler is going to be the probe and rinse speed, time in sample here. And under the analyzer tab, this is where you have all your timings for your peak. So you can copy the chart to clipboard. You can do a peak profile, and right here you can take and move that peak profile when it's done over to the worksheet log, so you can review it later. So all these are set in real time. You can grab these all these lines for the integration for the baseline correction point. You can grab them and move them, or you can toggle up, toggle down here, or you can just pop in there and type the number, and it's going to move the timing for that peak. So here's an example. So you take and set your pump speed, your gas flows, your sample uptake time, your rinse time, your integration time, and you just run the high standard. So it looks like this, and you very simply just go in and adjust all this stuff. And then on the bottom, it's going to give you a percent RSD for the peak profile. And then you can go ahead and grab that and send it into the log. So you can adjust all the timings there in real time. And then you can repeat it if you want to a second time to make sure it's still the same. So it's really a nice feature. It takes literally less than 2 minutes to develop a method. You put your pump tubing on, and then assuming after it's been conditioned. You go in and create your standards. You read your high standard, which is going to be your worst case scenario. You dial in your timing, everything for the peak plateau or peak area if you're doing that as well. And then it'll give you your percent RSD for the plateau. And then you're ready to go on to running standards and running your method. So the typical performance of this new tubing harness, it's basically about the same as what we were with the original tubing. So your IDL is less than 0.8. It's typically around 0.6 or 0.7 PPT. Your short-term precision is still really good at 3% for a 5 PPT, N equals 5. Less than 2 for a 20, N equals 5. Your response is about 40 microabsorbents per PPT. If we get into our PPB range, 0 to 20, set the gas flow to 100. The IDL is typically less than 0.2 ppb, around maybe 10, 12, or maybe even 8 ppt in that range. Long-term precision is still really, really good. 0.2 ppb is less than 2.5% RSD, N equal 40, and you have a response of about 13,500 per ppb. Under the normal tubing, this is going to be around 18 or 19,000 in response for ppb. So it's not a huge reduction, but if you look at the math, it's probably exactly that 33% less or 67% of what it was before. As I said, is really linear. So in order to validate the tubing, we ran two methods, US EPA 7471, which we all know is for RCRA, and it's soil sediments, deposit, and sludge site material. The calibration was from 0 to 10 ppb. The sample was about 0.2 grams in 50 mil. We did a block digestion. And then we also ran a US FDA method, elemental analysis, EAM 4.5, which is a microwave digest, and the calibration was blank up to 1,000 ppt or 1 ppb, so approximately 5 grams and 50 mils again in the microwave. Here's the settings for those two methods. 7471, uptake was 35 seconds, the rinse was 80, so that's a little over a minute and a half. Sample gas flow was 100, pump speed was 50, and replicate was 1.5 seconds with 4 of them. For the microwave digest, we were at 95 seconds, 30 and 65, and we were at 80%. So 3 mils per minute on this one, or I'm sorry, at 3 mils a sample on this one. Stannous chloride was 0.8 mils at 1.35 mils per minute, and then the flow was actually 5 mils per minute for the sample. Total waste was only 4 mils. On the microwave one, the US FDA method, approximately 4 mils for the sample at 8 milliliters per minute, because we were sampling for 30 seconds. And if you recall, it was 10 milliliters per minute at full 100%, and we're running at 80%, so it's very linear. So 4 mils for 30 seconds. If we went for a minute, it'd be 8 mils. Stannous chloride 1.1 mil at 2.2 mils per minute. Total waste was 5 mils on this. So here's the results, and what we analyzed was some standard reference material. So tuna, oyster tissue, mussel tissue, some coal fly ash, Tennessee River sediments, industrial sludge, and coal, which is a tough one to do by block digestion. So we kind of threw a big mix in there and just went after it. So here's the recoveries. Everything was really, really nice, as you'd like to see, kind of up and down, all within the statistical range for the samples. Nice recoveries all the way across for microwave digest and also the block digestion of the system. So some more of the results, we went out and got some salmon and some crab just from the supermarket, just as a nicety to run it and see what happened, because we were already doing the microwave. So basically, all the spike recovers are really good for those samples. And here's the concentration. The raw in the salmon was 0.011 ppm, and then when we convert to methyl, it was 0.0121, and then for the crab was also very low in methyl, 0.0084. So here's a fun fact: World Health Organization, tarbol uptake at 1.6. So we were well below any of that, and the average male at 80.7 kilograms could actually eat 1.29 milligrams per kilogram of methyl mercury. I think that's in a week as well. So well safe from the store salmon and crab for us to eat it. Some of the combined results for this system. So we have the lab control samples, the lab control dupe, and the salmon, the tuna, and the NIST samples for the block digestion. Here's all the spike recoveries all lining up. So the spike recoveries are really, really good for all of the samples as well. So this is sample and spike recovery. Application and tubing summary. So here's some of the app notes that we have on our website that have already deployed this new tubing. So we have larger notes, which we call application notes. We got beverages by microwave extraction, 7471, 7470 methodology, and then the original application that deployed all of the digestion process for the application of the new tubing. We have some technical notes down here. We have 2710, which is a soil by the system, and then we also have a 2711, which is a soil and also a wastewater. CA 7113 technical notes for the pump tubing. Here's a cross section of the differences, which is not huge, but 10 mils to 15, 2.7 to 5.7. But this is the big one right here, that 53% reduction in stannous chloride. And then the total waste is 40% reduction. Variable uptake greater than 0.83 mils per minute, and greater than 1.25 mils per minute at 100% on that flow as well. So the instrument detection limit for sure less than 1, less than 0.5. Typically this is around 0.6 or 0.7. So not a huge difference between that and the other tubing. Typical range change a little bit. Precision is relatively the same. The throughput is about the same, but at 0.5 we can't quite get it because we can't get that low with this new tubing. But in all honesty, most laboratories don't run at less than 0.5 ppt anyway, so it's really a non-starter. And here's the difference in response at the different flows. So with that, we offer a path for laboratories to achieve sustained sales, profit, and growth. Our systems meet the stringent method compliance. We increase sample throughput. That helps with ROI, so shortens that path, and limited daily maintenance. And here's a short cross-section of the 7600 and some of the applicable methods. There's many more than this throughout the laboratories that use the system with a myriad of methods as well. So that concludes today's webinar. I want to thank everybody for attending and listening to this short webinar on the new pump tubing. And I hope that you all go out and try the new pump tubing, save yourself some money, and you'll realize that the results are basically the same as before with the original pump tubing. So again, thank you.